meters an hour. So yeah, I'm looking forward to the old fox hunt. That should be a lot of fun, and it'll be great to have you up there joining us, Dave. It'll be bang on. We're from
40m CQ, Zulu Lima 40, Mike Victoria Lima. Zulu Lima 40, Mike Victoria Lima, CQ 40, over.
well set up. I've got my my little finder all going. I can remember the very early days, the first...
Oh yeah, let me turn that down. Yeah, g'day, it's Charlie ZL2CTM. Well, quite a bit has happened since I last put up a video, which I think was it yesterday or the day before? I think maybe the day before. I've finished off a few things and then converted the radio into a SSB. So, right. So how about we just start from the top, and then I can sort of talk through what I've been up to this morning in terms of tuning up the BFO and the like. So what you're just listening to here was the first on-ear checks of the radio after I've fine-tuned the BFO and the like. So anyway, let me just grab a couple of bits of paper which will explain what I've done over the last day or so, and we will go from there. So, right, where have we got our bits of paper? We have essentially finished off the last, the three IF amplifiers. So, in terms of, if I just go through the, I guess the RF chain here and talk about the new additions that have been added. So, you'll notice up here I've now got a reflective screen that's turned up to replace that backlit blue light. The really unfortunate thing is, from a dimensions point of view, it's probably a good sort of 5mm. In fact, let me just sort of zoom up a little bit there. The dimension of the screen itself is 5mm or so smaller than the existing screen, which is a bit of a pain because now when I put that screen into the Pelican case, there's a gap down either side of the screen, which is a little bit untidy. So I haven't quite worked out if I'm going to actually live with that or just stick with the blue one. To be fair, it wasn't too bad in bright sunlight. Anyway, so that's something which is turned up. Anyway, so RF is coming in. So this is a single conversions superhet. So RF is coming in and is going to the relay here. This relay is forming two functions. It is on one pole switching the RF, or the antenna, between the receive circuitry and what will be the power amplifier for the transmitter, and the other pole is switching the 12 volts hot, or the 12 volts that's coming in off the battery, between the receive circuitry and the transmit circuitry. So at the moment in receive mode, the coil is de-energized, so it's not drawing any current, and it's providing 12 volts to the receive circuitry. RF on the other case is passing through the normally closed contacts and into the bandpass filter. That's the filter we saw a couple of videos back. It's then going into the RF amplifier. No change there from the last video. What I have elected to do, because I do want to, and I'll just make a note here, a saying that everybody's heard: there's no such thing as a free lunch. So I just want to talk to that one. And I will get back to it. So the output of that is a 3dB pad, which is just padding the output of that amplifier before going into the relay here. Now this relay, you'll recall, if you go back to the first video, allows this IF chain here to be shared between the receive and the transmit circuitry. So rather than using bilateral amplifiers here in the IF chain, it's unidirectional. But rather than having one simple relay down here that basically switched the IF between the transmit and receive, in the past, with high gain in the IF stage, that particular configuration can quite often cause feedback because the output is very close to the input on that particular relay, and you tend to get oscillations. This configuration gets around that, and the output is always well away from the input. Anyway, go back to that first video and it sort of explains how that works, but it's pretty straightforward. So essentially the output of that RF amplifier is going into our mixer, and we have coming in off clock 0 of the SI5351 our variable frequency oscillator, our VFO, coming in on the LO port, and then the IF coming out of that is then being fed into our IF1 amplifier. So we have IF1, IF2 and IF3. IF1 is before the crystal filter, and IF2 and IF3 are after the crystal filter. You'll recall that I set up IF1 to also be 2 milliamps and 15 dB of gain. So that's exactly the same configuration as our RF amplifier up here. On the output of the crystal filter, where our bandwidth is now being constrained by the pass band of that filter, I've upped the gain, and I've upped the quiescent current from 2 milliamps up to 10 milliamps. So 10 milliamps for both of these are configured exactly the same, with 15 dB of gain. In between those two amplifiers is a 3 dB pad, and the output of this IF3 before going into our product detector is also a 3 dB pad there. So the output of that IF strip goes into our product detector. It gets mixed with our beat frequency, and I'll discuss how I set those up later on. And the output of that product detector is our audio, that one here. That audio is then going into a simple diplexer, which I'll also cover, and then the audio into our audio amplifier. So that's essentially the configuration from a hardware point of view for the. Let me just double check that. Nope, nothing to worry about. I think it's actually a scam, so I'll ignore that one. So that's physically how it's connected up. So got some choices now of how we're going to set up, or what I've done to set up the two frequencies coming out of that SI5351, the variable frequency and our beat frequency. So so just looking at the transformers before looking at the frequencies coming out of that SI5351. Got a number of transformers there just doing the impedance matching between the various stages. We've already discussed our RF amplifier here, that's 200 ohms up to 50, or down to 50 more the point. Our IF1 here, that is outputting 200 ohms up to 600 ohms. This filter here has got an input and output of 600 ohms. So there goes our IF1 output, 200 up to 600. And that gives us our 7 to 12 turn transformer here. The output of that crystal filter is 600 ohms, stepping that down to 50 ohms, and then the output is 200 to 50 for IF3. So there goes our 600 down to 50, and at the other end our 200 down to 50. So 4 turns to 14 turns. At the output is our same again, 10 turns down to 5 turns. And then lastly, the output of IF3 is 200 ohms down to 50 ohms for the SBL1. So again, funny old thing, 10 turns to 5 turns. So the next thing to basically make it all work was to set up the software to get the SI5351, the oscillator there, to output the correct signals for the two mixers, our mixer here and our product detector down here. So I'll try to depict that here. So before going any further, I did look at the second and third harmonics of the BFO and the like, just to make sure I wasn't going to have any issues with image frequencies and any out of band signals getting through our pass band here of the initial bandpass filter, and there weren't any, so I've basically decided to go with a high side insertion. In other words, our VFO signal is higher than our desired modulated signal down here, which I've just depicted as 7.1 megahertz in the 40 meter band. So this is our signal of interest. I'm just going to pick on 7.1 megahertz with our lower side band intelligence starting roughly 300 hertz below our nominated dial frequency, extending down another 2.7 odd, 2.7k. To give us our 2.7k audio bandwidth. Gosh, a terrible way of saying it, but you know what I'm talking about. So when that signal there is fed into our mixer here and mixed up to the IF, we get two lots of sidebands, an upper sideband and a lower sideband, and we want to position the unwanted sideband outside of the filter. In other words, we want to put inside the passband of our crystal filter the desired sideband, which will then get processed and dropped down to baseband in our product detector, in other words down to our audio frequency. So because I am using high side VFO, I need to have the BFO sitting on the low side of our crystal filter. And why that is because when you subtract from our unmodulated VFO our modulated signal, we get sideband inversion. So it turns out at the IF our desired sideband is sitting, it's the upper sideband of that IF. So we want to have our upper sideband sitting inside the passband of the crystal filter, and on the outside would be, and therefore being attenuated, is our unwanted lower sideband. So we are getting sideband inversion as a result of having a high side VFO. So in order to make it all work, we need to work out what that BFO frequency is going to be. So this particular crystal filter has a center frequency of 8.83 megahertz, and 6 dB down it is 2400 hertz according to the spec sheet. So what I have done, I have found this point here and then extended it another 300 hertz to take into consideration that our desired information on the our wanted signal is already 300 hertz, or starts at 300 hertz away from the dial frequency. So that's what's depicted here. So 8.83 megahertz minus the bandwidth divided by 2, so half the bandwidth, and then shifted another 300 hertz. So that comes out of a beat frequency of 8.8288 megahertz. So that's what's been put into the software to come out of clock 2. Clock 1, or let's say again clock 0, which is our VFO, that's this one sitting here. So that is just simply the desired frequency, in other words what's being displayed on the screen here, plus our beat frequency gives us our VFO. So as this varies up and down in sympathy. And that's all I have done to do that. The other thing was just to do a little bit of fine tuning, and in the end it was pretty well spot on. So that's, you could say that's a coarse determination of what the beat frequency needs to be, but then there's a matter of then fine tuning that either by ear, so having a listen to the received signal and does it sound natural and the like, or another means. What I've done it both through the ear but also using the SIGGEN up here. So we'll just to change the angle. Right, so what I've got going on here, and what I'll do, I'll just swap over. This is interesting. Let me just turn the volume up. And I'll just tune off. So there goes our atmospheric noise on 40. Now if I was to unplug that, it drops right off. So that's good. So the internal noise is certainly acceptable, so I'm more than happy with that. Let me just turn that down and remind me to talk about no such thing as a free lunch. So I've now just plugged in the we'll just do the cheat, so I'll just reset that, and that'll bring us back to 790. So we have the SIGGEN sitting up here. I've got a level of minus 50 dBm, and I'll come back to that, and a frequency of 7.09 megahertz. So if I was to, and I have got the RF turned on, we should have nothing coming out of the speaker because we are zero beating. If I was to offset this, in other words, I'm now going to, rather than have a modulated signal to create that lower sideband, I'm going to give the radio a carrier wave, set off or offset more the point to what I'm tuned to by a certain amount, and that's the same as the intelligence in that sideband. So if I start to set down, we start to see a tone coming in. So that tone, I'll just turn it down so it's not too loud in the speaker. So what I'm doing now is I'm just, if I had another bit of paper here. Oh, where's that bit of paper gone? Never mind. So you can see here that the frequency is now 89.7. Let me just go back. 89.7 megahertz. So 0897 megahertz. In other words, 300 hertz down from 7.09 megahertz. So that's our our lowest frequency that we want to be able to pass through our passband, because in order to have good intelligible speech we want to have at least, well, I shouldn't say at least, that's sort of roughly 300 hertz to 3 kilohertz roughly. So I want to get definitely the lower frequency being adequately passed through, and the upper frequency. Noting that this crystal filter down here is 2400 hertz. So I'm wanting to get sort of that 2700 at the higher end and 300 hertz at the lower end coming through. So I'm just scoping the output of the audio amplifier, and I'm just going to take a notional number here of 360 millivolts. So peak to peak doesn't really matter. It's just getting the relative amplitude. So that's 300 hertz down. If I was to now to continue, and I wish I could find that other bit of paper. Here it is. There it is. Something I prepared earlier. So you can see here 300 hertz down from our dial frequency is 89.7, which is up there, and I'm now going to drop that down to 2700, which is going to work out to be 87.300. So as I drop this down, not too loud. See, I've just ruined it. What an idiot. Let me go back to 89. I just don't want to have it too loud for the speaker, so it doesn't really matter too much. We're just going to have to set this on, I don't know, roughly 300. That'll do. Close enough. It's going to get a bit noisy, and I apologise for that. I'm going to decrease this down to 2700 hertz below our 7090 kilohertz to get that sort of the highest frequency that I want to be able to pass through that IF. You can see the amplitude comes up, and it's going to be 87.3 to 87.3. So that's now the highest frequency, and it's 264. Coming back in the other direction. And coming down and down and down. So 89.3. So back down to 600. So we've got a little bit of attenuation at the higher end, so it wouldn't be that difficult then just to now move that beat frequency just to shift ultimately through that first mixer where that passband is sitting. I did that before and I was actually quite happy where it is, so I'll go and double check it after this video, but that's just a quick easy way just to determine whereabouts your audio is sitting. You could put in the, no, I won't go into that. Anyway, so right, what did I want to cover off? So I did want to talk about there's no such thing as a free lunch, and what I mean by that is I have made a decision because of the available space in the Pelican case and the fact that I'm still using through-hole components, that I'm limited for space. So even though I am intending to have some vertical pieces of double-sided copper board with circuits on both sides to try and maximise my space, I am space limited. So as a consequence, I made a decision not to have a AGC circuit in the radio. Yeah, full stop. I am going to build another rig straight after building this one. I'm going to build a base rig, and I'm going to make that with AGC so I can explore further. I did it some time ago, but I wouldn't mind revisiting it AGC, because, right, why is AGC important? So if we were to go back up to 89, that's 709, so a zero beating, let's come off like that terrible 1K sound. So we're now 1K down. So if I go back to level, let's just so at the moment that's a minus 110. I can just, you can just see it there and no more. So it actually goes down to minus 115 is what I'm determining is the minimum discernible signal. So the signal that I can still hear. Now, is that producing a certain signal to noise ratio in the output? Of course not. But I'm just, like I say, the minimum discernible signal for this particular radio, as far as my interpretation, is about a minus 115 dBm. Anyway, so the issue you have, and I'll keep dropping the volume as the signal comes up, minus 40 dBm is pretty well a pretty loud signal. Sorry about that, that's awfully loud. Is a, gosh, it's going to sound terrible, I don't know quite sure how it's going to sound in the video, but that's a pretty strong signal. If I then was to go to say minus 30, you can just start to hear a little bit of distortion coming in where we're starting to overdrive the amplifiers in the circuit. And you can just start to see a little bit of distortion coming in on the signal. Go back down to minus 40 and we're starting to get more into that pure sine wave. You can hear the those other high frequency components dropping off. With an AGC circuit, I wouldn't have to worry about that because as the signal got stronger and stronger, the gain of the overall radio would be dropping down. So I wouldn't have so much problems with overloading. Now in this particular case, it'll be interesting to see. Like I say, minus 40 dBm is a pretty strong signal coming in. Certainly in my local area here, not an issue. And where I guess I'll be intending to operate the radio, it shouldn't be an issue anyway. But suffice to say, no such thing as a free lunch. And like I say, I do want to build another radio after this one to explore a bit more having an AGC circuit to get around that particular issue. So enough said there. Let me just turn the RF off. So what else do I want to talk about? So we talked about the configuration. We've talked about, so I had tons of gain when I first put this together and configured it. So I elected to, which is good practice anyway, to include those 3 dB pads. A lot of people use 6 dB. I've elected to use 3 dB on the outputs of the amplifiers just to provide a stable load for those particular amplifiers. This one down here is actually a 600 as an input to the input to that crystal filter. The diplexer here, pretty straightforward one, very simple for audio. So an L and a C with our 51 ohm or 50 ohm resistor there. I was initially looking at that sort of 3 to 4 kilohertz cutoff for this particular diplexer here, but that was going to result in a sort of into the millihenries inductor, which I didn't have. So what I elected to do was just use some inductors that I had on hand, these little green ones down here. So I've got 2 in series, so 2 330 microhenry inductors. So it comes out at 660 microhenry. So I've just plucked that one, and then I've rearranged the formula that would ordinarily give us inductance based on the frequency. So I've just made frequency the subject, so move that up, put the L down, and that comes out at 12 kilohertz, as we can see here. Now I'm going to deem that to be okay at this stage of the game. So based on 12 kilohertz, I can then work out, or based on 12 kilohertz, what does that mean for a capacitance, which we see down here, and it comes out at 264 nanofarads, and I've just selected the nearest standard value, which is 0.22 microfarads, or 220 nanofarads, and that's that capacitor there. So that's just providing that load to the product detector before feeding the audio into our audio amplifier. So that's covered off on that one. We talked about the gain of these various stages and the quiescent current. That was worked out, I think, on video 2 when I used those large formulas that I put into the spreadsheet. And again, public service announcement. I'm no expert in this. This is just my way of doing things. It's not necessarily the right way. It is a way. It's certainly not the best way, but it is a way. So I'm going to say that again. So I'm going to now, what I might do tonight before I put this video out, no, I won't. What I'm going to do now is move on to the transmitter. So I'm going to start by the microphone amplifier. So the microphone amplifier is going to be fed into this mixer down here, and on transmit this will become our balanced modulator. So actually in transmit the Arduino will sense that it's in transmit and will actually invert the outputs of clock 0 and clock 2. So clock 2 will actually now output the VFO, which will become the carrier oscillator. That'll upstep our IF, but more importantly out of clock 0 there will be our beat frequency. That'll mix with our audio coming in from our microphone, and then out of that, which will then feed into the IF chain, will be our low level IF. Out of that will feed into our carrier oscillator over here, and then that'll be stepped up to our desired transmit frequency. So out of here we'll go through the non-existent at the moment power amplifier before exiting out the relay as transmitted high power. Noting it's going to be a QRP rig. So I will be looking to more than likely insert a post-mixer diplexer for RF. Thinking about using this circuit here, which is a well-known circuit. I'm going to choose a Q of 10 for HF, and through the formulas which I like to use, as I've mentioned several times, calculate the various values for that particular diplexer. So that'll be another one to work out. And I think, as I've said many times, there's absolutely no script in these videos, it's just me yabbering away. I think that pretty well covers everything. I will say, which is nice, no whooshing sound with the rotary encoder. That's buttery smooth, which is really nice. No birdies, which is really good. I have had in the past up at the higher end of the 40m band a birdie, but I don't have that at all in this particular configuration, which is nice. So that's good, and all in all pretty happy with how it's turned out. So I might just sort of do a bit more tinkering around just to double check that that BFO frequency is spot on. I'm pretty happy with the way it's sounding, certainly on ear, and using the SIGGEN and scoping the output, it's pretty close, so I don't think I'll be doing too much more on that. So all good. Anyway, I have rabbited on way longer than I thought I was going to, so 73, and I will see you probably for the microphone amplifier, which will then probably tie in with low power, because out of here will be low power single side band transmit, so we'll be able to pick that up on the radio just to get an idea of how that's sounding before we amplify it up for high power. Rightio, 73, cheers, see you soon.